Fourier series. So Fourier representation of the signals we know. Fourier series representation of signals. So Fourier series is a frequency domain representation. As we already know, the Fourier series is found with the continuous time signals. Let's consider a continuous time periodic signal, and the periodic signal will be any fundamental period. Let's say its fundamental frequency is given by omega naught is equal to 2 pi by t, or let's say t naught. And we know the signals are periodic when they repeat themselves after a certain interval of t. Then in Fourier series representation, we need to learn both of these equations. The first one is referred as the synthesis equation, and the second one is referred as the analysis equation. The synthesis equation states that x of t is equal to summation k from minus infinity to plus infinity x of k e raised to j k omega naught t. And the next one is x of k. The equation is written for x of k. It's referred as the analysis equation. So the analysis equation is this way. It is x of k is equal to 1 by t, where t is the fundamental time period of the signal x of t, then integration over the time interval t. So all the samples, or whatever is the one time interval of the x of t is there throughout that first period. It may be any of them. It may be from including 0 onwards, or one period of the signal is considered. The integral over that one period x of t e raised to j k omega naught t dt. This is the synthesis equation and analysis equation, and by using this we need to learn, in this Fourier series we need to learn some properties, the properties of Fourier series. They are also important, and the problems. So we'll see the properties of this Fourier series. So the properties are this way. The properties of Fourier series. So properties of Fourier series are linearity, time shift, frequency shift, scaling, time domain differentiation, convolution, modulation, Parseval's theorem, and regarding symmetry. So let's learn what are these. Linearity. So in learning this linearity, we need to consider two signals. Let's say x of t and y of t are two signals, and x of t is Fourier transform with omega naught as its fundamental frequency. X of k is its Fourier transform and Fourier series and Fourier domain representation, and y of t's Fourier domain representation is y of k. So after taking the Fourier series with respect to omega naught as its fundamental frequency, we are getting y of k. If x of k and y of k are the Fourier representations of x of t and y of t, then z of t, let's say z of t is the weighted sum of x of t and y of t signals. Then the Fourier transform of this weighted signal is equal to a into the Fourier representation of the x signal plus b into the Fourier representation of the y signal. So let's prove this well. This x of t and y of t have fundamental period. T is equal to 2 pi by omega naught. Omega naught is equal to 2 pi by t, or t is equal to 2 pi by omega naught. Then how to prove all these properties? So these all are proved with this analysis equation. So we'll be considering the analysis equation, and let's say x of k is one of our component, or it is one of our signals. So we have considered we'll consider z of k as the signal, and z of t is the weighted sum. When we substitute the value of this x of t in this equation, what all happens? So by using this analysis equation itself, almost all the properties are being derived. So let's see the proofs of all of them one by one. Now let's consider the analysis equation x of k 1 by t, the integral over t x of t e raised to j k omega naught t dt. Now in this equation, and x of k's Fourier representation is this one, means in place of x, y if it is, means in place of x of t, not necessary that always x should be the signal. So we can have y of t. In those cases, these equations will be corresponding to y. So x of t signal Fourier representation is this way. It's analysis equation, and analysis equation of y of t signal is this one, or these are the Fourier representations. Now if we write the equation for z of k, it would be same 1 by t, that's it. Here z of k is there, so zt e raised to jk omega naught t dt. Now what is the zt? Substituted from here, as zt is a into x of t plus b into y of t. So when we substitute that, now zt is being substituted, it's a simple proof, e raised to minus jk omega naught t dt. Now just as we know, these bracket things can be written in a separate way. So integration satisfies the distributive property. So 1 by t, a is a constant, let's take it as outside, the integral over the time interval t x of t e raised to minus jk omega naught t dt, and the same 1 by t b. So just this bracket is being, these components are multiplied individually, integration is applied to individual terms, so we get these terms. And when we compare this term with the first one, so it is nothing but x of k, except this a, everything what all we need to represent x of k is present, and y of k also. So z of k is equal to a x of k plus b y of k. So the properties are important because at least 2 of the properties will be asked in all exams. So I hope linearity is understood. Then the next one is the time shift. So time shift signal, we all are familiar with the time shifted version. The signal x of t minus t naught is the time shifted version of x of t. Hence a time delay or a time advance is referred as time shift. So x of t and x of k are the Fourier and time domain pairs. When these are so, with the omega naught as its fundamental frequency, then let's say w of t is the time shifted, and here x of t is shifted by t naught units. So x of t minus t naught. When we apply this x of t minus t naught, then what's the result will be expected? So it would be e raised to minus jk omega naught t naught x of t. Let's see how can we obtain this. Now let's write the analysis equation as we all are known that. And if we write the analysis equation with w, it's same. Now what we do is, in this, substitute the value of this w of t. The value of this w of t is x of t minus t naught. X of t, will substitute this w of t. W of t is nothing but x of t minus t naught. So when we substitute this w of t as x of t minus t naught, our equation for w of k becomes this. Now x of t, this equation, if we need to write the Fourier representation of Fourier domain kind of a representation like x of k, we should have only one term here, so that this equation, the Fourier equation, so it should be x of k is 1 by t, x of t e raised to jk omega naught k. So it should not be like t naught and all, and t minus something and all. We have to make it like a single letter. So x of t, and that letter should be there in our e to the power, whatever is the e to the power is there. So for that, we need to make this t minus t naught as a single term. For that, let's take one variable. It can be anything. Let's take up some other value for this t minus t naught. So let t minus t naught equal, let's say, yum. If it is equal to yum, then this equation becomes, this one is same. Now x of yum, it would be now e raised to minus j k omega naught, fine. Now t. This t is nothing but yum. This t naught has to go on this side because value of t naught, t has to be by using this equation. Now e raised to j k omega naught t becomes, up till omega naught no change, but the value of t is yum plus t naught. So that way, right. And this one is t. So integration is with respect to dt. Now with respect to dm, dm is equal to dt. So we write dm in place of dt. Nothing changes, same things would be there. Now e raised to minus jk omega naught yum. Now to make it as a standard form of analysis equation, we should have this, whatever is this term, e raised to jk omega naught yum. This t naught is extra. So we take this e to the power minus jk omega naught t naught outside, and 1 by t, this all remains x of yum is to minus jk omega naught yum dm will be there. And when we expand this term, except this exponential, it is nothing but rx of t. So this is the proof. The Fourier representation of x of t minus t naught is nothing but e raised to minus jk omega naught t naught x of 2. Suppose if we are in need of finding what is x of t minus 2, then it would be e raised to minus jk omega naught 2 and x of k. So this property would be helpful in some places, and we can use this property whenever it is required. Then the next property, the third one, is frequency shift. So this is time shift, means the signal, time domain signal is shifted, and this causes a change in the frequency domain signal. So it is multiplied by e raised to minus jk, whatever is the shifted value. Then if we do the frequency shift, what would be the change? That is our, like, we want to understand. Let's consider the x and x of t and x of k as the Fourier pairs, Fourier and time domain pairs, with omega naught as its fundamental frequency and t as the period. And frequency domain, frequency shifted signal means, what is the frequency? Frequency is e to the power j k naught omega naught t naught. Now k is frequency change, so we need to multiply our signal x of t with e raised to j k naught omega naught t. When we do the multiplication with e raised to j k naught omega naught t with x of t, what signal we produce? That would be x of k minus k naught, and we need to prove this one. How does this happen? So for that, let's consider the analysis equation, and let for g of k the same representation be this. Now g of t has to be substituted from this. Let's substitute g of t as e raised to j k naught omega naught t x of t, and the rest is same as it is. Now this e raised to j k naught omega naught t. Now let's write x of t, and we have e raised to minus j k omega naught t, and here same, e raised to j is there, omega naught is there, t, except this is k naught here and here it is k, and this is with minus and this is with plus sign. So we can write this one as x of t e raised to, and remember we need to write it as e to the power always minus, because our x of k is having the minus term. So e raised to minus jk, and this one minus k naught. If I write minus k naught, again when we expand it is the same term. minus of minus would be plus, and this t. So in the bracket k minus k naught will come by including this term with this exponential into dt. So this is nothing but x of t. So here in analysis equation, this x of k is nothing but whatever is there, the multiple means x of t e raised to minus j k omega naught t. Here whatever is there, this k is nothing but here whatever is the multiple of j omega naught t. Now multiple of j omega naught t is what? J omega naught t's multiple is j omega naught t's multiple is k minus k naught. So it is x of k minus k naught. Now next property is scaling. Scaling, if x of t and x of k are Fourier and tandem and pairs, then x of at is the scaled version. A can be anything, and here we choose a greater than 0, because when a is less than 0, the signal would go in a reverse fashion. So x of at is greater than 0. If it is greater than in between 0 and 1, then x of at will be the expanded version of x of t, and if this a is greater than 1, then it is a compressed version. If x of t is like x of at, if a is equal to 2, then the x of t signal, if it is having its fundamental period as t, then x of 2t will have its fundamental period as in this way. It will be t by 2. Now let's write the analysis equation x of k, and we go for solving what is the scaled versions for your series. So t is equal to t by a. The fundamental period will change as t by a. The integration also, as the period changes, so integration value would be from over t by a, one period value, z of t e raised to j k a omega naught t. Omega naught is equal to 2 pi by t, but as our t has become t by a, omega naught value would be 2 pi into a divided by t. By substituting the same, we get this one as x of at e raised to minus j k a omega naught t. So a gets multiplied with this. So the value is, it is omega naught into a. So e raised to minus j k a omega naught t dt, and this a is taken up. And to remove this at, as we should have only one term, let's remove this at. So by taking m, at is equal to m, and the differentiation of this one is a into dt is equal to dm, which makes it as 1 by a dm. So by substituting this in z of k, we get a by t as it is, integration over t by a interval. Now x of m, it would be e raised to minus j k omega naught m 1 by a dm. So we get as here at is equal to m we have taken. Now this a and t is equal to m minus j k omega naught. At is nothing but m, and dm dt is replaced with 1 by a dm. This a and this a we can cancel. The equation will be like just again 1 by t x of m e raised to minus j k omega naught m dm, which is nothing but z of k is equal to x of k. So even after scaling, the Fourier transform will not change. Indicates that the scaled version too has the same value of Fourier series as the earlier version or the original version. Then the next property is differentiation, time differentiation. So here we consider x of t and x of k signals, and the differentiation d by dt of x of t's Fourier series is j k omega naught x of k. Then how does it's possible? Let's see. So for this we consider our this x of t, the synthesis equation. X of t is equal to, we know, summation. This first equation we consider e raised to j k omega naught t. So after considering this first equation, now what we do is we go for differentiating that equation. So when we do differentiation, we can write it as d by dt of x of t is equal to d by dt, as differentiation has to be applied to on either side. So d by dt summation k from minus infinity to plus infinity x of k e raised to j k omega naught t. Well, right. Now this side will remain as it is, the left side, but on the right side, d by dt, there is a term like e raised to j k omega naught t, and this t is certainly going to change once we do the differentiation. So x of k summation k from minus infinity to plus infinity x of k as it is, let's apply, because this all is independent of that differentiation because there is no t. Let's do the differentiation with respect to this term, and when we take it inside that summation, it goes to a particular term. So let's make it as a partial derivative, dou by dou t of e raised to j k omega naught t. When we do the differentiation of this, we know differentiation of e raised to j t or e raised to j term is nothing but this, whatever is the coefficient of that one, multiplied by again e to the power same term. So e raised to omega t's differentiation is omega into e raised to j omega into e raised to omega t. So we write this one j, whatever is except this k, j k omega naught e raised to j k omega naught t. So this term is j k omega naught x of k e raised to j k omega naught t. So this term is independent of this term, we can take it outside. So it is independent of this equation also, j k omega naught. So j k omega naught will take outside, and this summation will be for x of k e raised to j k omega naught t, which is nothing but this same. So we can write this one. Now e raised to, by comparing this equation with the synthesis equation, we can write now this x of k e raised to, now x of t's representation is x of k e raised to j k omega naught t. If it is d by d, if it is of d by dt x of t, then this term is extra, other than whatever is the expansion of x of t. So x of t, d by dt is x of d by dt of x of t is this term j k omega naught and this x of k itself. Means the Fourier representation just gets multiplied with whatever is j k omega naught to the Fourier representation. So d by dt differentiation in the time domain will multiply its Fourier representation with j k omega naught. Then the next one is the convolution. As we are already familiar with convolution, x of t and x of k, similarly to find the convolution we need two signals. So let's consider another signal y of t whose Fourier series, Fourier representation is y of t, and let's take the Fourier representation, let's take the convolution of x of t and y of t as z of t, and what it will result in the Fourier series. Let's see. So it would be multiplication. The convolution, which is the complex in the time domain and which has to be found with different steps, in the time domain. In the Fourier domain, it is just multiplication. Means if I have both the signals, time domain signals, and if I have to get its convolution, then there is another way also. What I can do is I can get the Fourier series of those both the signals individually, and then I can multiply it. And if I multiply, after multiplying, if I multiply it by means of a time period, then I'll get whatever is the Fourier domain representation or Fourier domain signal of that convoluted one. If I need that signal in the time domain itself, again I can go for the reverse process from Fourier to time domain, that is inverse Fourier process. So we'll get whatever is that signal. So Fourier makes lots of mathematical calculations in the time domain easier, and the convolution is just a multiplication in case of frequency domain. So to prove this, we consider both the signals, their analysis equations, and we consider z of the signal. It is 1 by t, z of t e raised to j k omega naught t dt. Now 1 by t, the integration x of t, let's substitute the convolution, x of t convolution with y of t e raised to minus j k omega naught t dt. Now to solve this one, we know how the convolution is given. We know convolution of signals x of t and y of t is nothing but it is x of tau h of t minus tau. In the similar fashion, we are not using the tau variable here, let's use L in place of tau. Then this x of t convolution with x of y of t will become x of L y of t minus L. Just tau is used in place of L is used in place of tau, so it is x of L y of t minus L dl. So this convolution is replaced with its equivalent equation, and we know convolution leads to, the convolution has its own integration. So let's write this L is L over the t we write. So xl y of t minus L dl, and this multiplication is as it is, and this 1 by t is as it is, integration as it is. So this convolution is expanded, convolution is integration x of L y of t minus L dl. Just we go on rearranging. We can take this, we can exchange these integrations. So let's take the second integration first, and let's write x of L. Let's take this second integration then. We can take this x of L outside, because for this t, there is no term here in x of L that is corresponding to t, so we can take it outside. And integration t is equal to tau. So over this integration, and within this y of t minus L has to be there. We can't take it outside because the t is, this y of t minus L is depending on this integration value. Now e raised to minus jk omega naught t dl dt is there, and we know that we should have a single term here. So let's substitute this t minus L as m. When we do that, dt is equal to dm, the differentiation, and this part would be as it is. And this, when I substitute this t minus L as m, now this becomes m, this integration, this t minus L is equal to m. Now this t is equal to, over the period t it is. So now this becomes, this L is for t, this m, now in place of t minus L we write, in place of t we write m, and this y of m e raised to minus jk omega naught. What is this t? It is nothing but m plus L. Let's do that, and we know this has given dl and this is given dt, but by this integration, what is dt? dt is equal to dn. And now we can go for solving this. X of L is there with this, as we can expand this e raised to minus jk omega naught. Let's take L here, and with this integration, which is with respect to m, let's use m, and when we split them in this fashion, we can write this 1 by t as it is, and t into here x of k. To write the equivalent terms of this, we know this integration equations are in this way: 1 by t x of t e raised to minus jk omega naught is x of k. So here in both of those terms, the t 1 by t is not there. This 1 by t is missing. So we can write, if this integration is there, then we can write this one t into x of k is equal to this integration value. So by using that, we can write this one as t into x of k, and we can write this as t into y of k. So that t square into x of k y of k and 1 by t is there. So the result would be t into x of k y of k. Then the next property is modulation. So modulation is nothing but multiplication in the time term. So modulation is multiplication, and the result of multiplication in the time domain is convolution in the frequency domain. So let's see what will be the result. We need two signals for it, as we already know. Let's take z of k, which is z of t e raised to minus jk omega naught t. Now z of t is x of t into y of t. Let's substitute it: e raised to minus jk omega naught t dt. Now to solve this one, x of t, we use the synthesis equation. So x of t, let's do it with a different variable, because already the t is being, already the k and all are to be used. So let's write it with L. L from minus infinity to plus infinity, the same equation. Now x of t is equal to k. With respect to k, it is written, just replace L wherever there is k. Then this equation becomes L from minus infinity to plus infinity, x of this L, k is not there, e raised to j, L, k is replaced, omega naught t. So just we are writing the synthesis equation, and let's substitute this x of t here. So after substitution, we get in this way. The equation takes up this form, and in this, let's take up this integration. Let's exchange this integration and summations. So summation x of L we can write, because with respect to this L only, x of L is only within this summation. Integration with respect to t, it is independent of, and integration y of t e raised to minus j k. Now here these two terms we can merge, and when we merge it, it is e raised to minus j k minus L omega naught t and t dt. And now this can be written as, it is summation, this 1 by t, we'll take it here. Let's say it is before this integration. Then summation x of L it is, and this integration will give from this y of t e raised to minus j k minus L omega naught t. So if we have this term y of t, this term, and the same is there here, then the x would be what? X would be whatever is there here. It is just like x of k minus k naught we have written in a similar fashion. Here it is x of k minus L. So we can write y of k minus L. So this is nothing but the expansion of convolution. So which can be written as x of k convolution with y of k. Then the next property is Parseval's theorem, which is the most important property, and many of the times it was asked in the exams. X of t, let's consider two signals here. X of t, this Fourier domain representation is x of k, as it is a periodic signal with omega naught as its fundamental frequency and t naught as its or t as its fundamental period. Then, as per the Parseval's theorem, it says that 1 by t times the integration over the interval t, the magnitude of x of t square dt is equal to summation k from minus infinity to plus infinity, the magnitude of x of k square. So this is the Parseval's theorem. So we need to prove this one in the problems. It would be more clear in those cases. So let's go for proving this one. So Parseval's theorem, or sometimes it is referred as power theorem also. So we know that the average power of the periodic continuous time signal, as it was dealt in the first by learning the power and energy signals, P is 1 by t integral over the duration time x of t, the magnitude square dt. Now just we expand this. This x of t can be written as x of t star t, where x of t and x star of t are complex conjugates of each other. We know what are complex conjugates. So for example, x plus jy is there, just for example, x plus jy is a complex term. Then its complex conjugate is x minus jy. These two are referred as the complex conjugates of each other. And the magnitude of these is always same, because root of x square plus y square is the magnitude of both of these. Then here x of t and x star of t are the complex conjugates, just like the one we saw, x plus jy in that way. Now this x of t, we write the expansion of this complex conjugate, k from minus infinity to plus infinity. Now complex conjugates representation in the Fourier domain, let it be x star of k, now e raised to, so which will be written, now x of t's representation, synthesis equation it will have e raised to j k omega naught t, but it is a complex conjugate. As it is a complex conjugate, let's assume that it's imaginary. It's imaginary means e raised to j k, j term, it is minus. A real term will be same, but imaginary term is with a minus sign. So by considering that, so we are writing minus sign here. It is e raised to minus j k omega naught t, because it is a complex term, complex conjugate term. dt, when we solve this, p is equal to 1 by t summation. Now we take this outside the summation and integral is taken inside, x star of k, and this is x of k e raised to minus j k omega naught t, which is nothing but x of k. So which gives us summation k from minus infinity to plus infinity, x star of k, x of k, so which is the magnitude of x of k, the square. So which proves the same thing, that is p 1 by t. With this we started and we arrived at the other one, which is nothing but the Parseval's theorem. So this is regarding the properties, and we can see the problems in the next video.